topic of today's lecture is linear regression. This is chapter 10 in the textbook. Before we begin, let's do some basic revision. A few weeks ago, we learned about measures of central tendency. A measure of central tendency is a single value that best represents or summarizes your data. And we learned about three such values. They are the mean, the median, and the mode. The formula for the mean is represented in the box in front of you. You're probably most familiar with this formula already because this is something that you've been working with the whole time. The mean is also known as the arithmetic average, so whenever you calculated your average at school, this is basically what you were doing. The formula reads x bar equals summation of x divided by n. That uppercase Greek letter is called sigma, and that means add or summation. It means add up. So what we're doing is we're adding up all the scores and we're then dividing it by the number of scores that we have. Notice that this formula is for x bar, in other words, the sample average. If you were calculating the population average, then you would be calculating mu. We can also calculate the average from class intervals. In other words, we don't need to use the individual raw scores, but rather, if our scores were classified into groups of data, like for example 0 to 10% and 11 to 20%, then we can calculate the average from those class intervals as well. You would have learnt about this in the tutorials. The second measure of central tendency is the median. The median is the score that's the 50th percentile of the distribution. The median is best to use when your data could be skewed. For example, if we were looking at the winnings from a lottery or from a casino. It's very unlikely, unfortunately, that any of us will probably win the lottery. Instead, we may only win R2.50 or R6, one of the lower values that most people win. If we wanted to calculate the mean for this data, it may be very high because the person who wins R60 million is going to pull that average up. So instead, what we may want to calculate is the median. This is a score that falls right in the middle. If you're looking at a box plot, the median is the bold line that's in the middle of, well, it's not always in the middle, but it's the bold line that's in the box. The last measure of central tendency is the mode. The mode is the value that occurs the most frequently, and this is the only measure of central tendency that you can use for nominal data. You can think of the mode as the value that one would use for voting. If you went to the elections, and you wanted to vote for a political party, then what they are typically counting is the mode. It's which party was written down the most frequently or voted for the most frequently. The next chapter that we went over was measures of variability or variation, and this is how the data is spread within the data set or distribution. We looked at three important ones. They are the range, the variance, and the standard deviation. We did also look at the average deviation, and this is covered in the textbook, but it's not as important as these three. The range is the easiest one to calculate and to understand. It's the difference between the maximum value and the minimum value. For example, their weight ranged from 20 kilograms to 80 kilograms. The problem with the range is that it only includes the maximum and the minimum. So you can't comment on the rest of the scores. You would have no idea how the rest of the scores are spread out within the distribution. For all we know, the rest of the scores could be just below the maximum, or maybe they're just above the minimum, or they could be clumped together around the mean. It's just not clear from the range, and that's one of the disadvantages of the range. The next type of range that we learned about is the interquartile range. This is the middle 50% of the scores. We calculate the interquartile range by taking the value at the third quartile and minusing the value for the first quartile, and then we get the middle 50%. This is one way of dealing with outliers, which we assume are falling within the two tails that we are excluding. The next type of measure of variability that we learned about is variance, and the variance is the first step towards calculating the average difference or distance between each score and the mean, or how the scores differ from the mean on average. So if you look at the formula on the board or on the PowerPoint, there's a formula for the sample variance and for the population variance. The numerator for both of them has the summation of the difference between x and x bar or mu, and that has been squared. Now let's just pretend that we ignore the squared, okay? Just say that there's no square there, and you just had to calculate the difference between x and the mean, and then you add up all of those differences. If you did that without manipulating the difference or the distance in any way, you would get a value of 0. And the reason why is because some of the scores are below the average and other scores are above the average. If you add them up, they equal to 0. So the one way that we deal with this is we square the differences and then we add them up. So that's why you have this square in the formula. The average deviation doesn't have that. It handles that difference differently. It just makes the values, the differences or the distances, absolute. After you've done that, you will then divide the numerator by the denominator. Notice that for the sample variance, you are dividing by n minus 1, but for the population variance, you are dividing it by n. To calculate the standard deviation, you just square root the variance. What I want you to notice is that anything for the sample is represented by Roman or Latin letters, so the S in this case, whereas for the population it's Greek letters, and this is sigma. When you square root the variance to calculate the standard deviation, you are then able to use the original unit of measurement. So for example, if our data was weight, then obviously everyone's weight in our country would be measured in kilograms. The standard deviation could be, for example, 2 kilograms, but the variance would be 4 kilograms squared. It doesn't really make sense to talk about 4 kilograms squared. What is kilograms squared? So instead, we calculate the standard deviation, and this allows us to use that original unit of measurement. The variance and the standard deviation is very important for the types of statistical tests that we do later, which is why we focus on them. The next topic that we looked at is probability. Probability is the chance or the high likelihood of something happening, and probability ranges from 0 to 1. It cannot ever be less than 0, and it cannot be more than 1. We normally represent probability as a decimal, but we can represent it as a fraction or a percentage. Obviously, if it is represented as a percentage, then the maximum value for probability is 100%. But that doesn't mean that suddenly probability can be more than 1. The 100% is just the percentage representation of the value 1. If you know what the probability is of something happening, then that probability plus the probability of that same thing not happening must be equal to 1, because it's exhaustive. So for example, if I toss a coin, there are only 2 outcomes, heads or tails. The probability of it landing on heads plus the probability of it not landing on heads must be equal to 1, because one of those 2 things will happen for definite. That means that you can manipulate the formula in point 2 to calculate what is the probability of something not happening. So, for example, if the probability of my coin landing on heads is, just pretend, 0.4, then the probability of it landing not on heads is 1 minus 0.4, in other words, 0.6. The formula for probability is A divided by N. A is the number of successes or the number of outcomes that will count as a success divided by the total number of outcomes. There are 2 types of probability. The one is theoretical probability and the other one is empirical probability. Theoretical probability has its origins in game of chance. The empirical probability has its or is calculated from actual data and from observations, and they can differ from each other. So for example, if you were to toss a coin, technically the probability of it landing on heads or tails is 0.5. That is a theoretical probability. But it might just happen that if I toss my coin, it's not going to land on heads as often as it should based on the theoretical probability. It could land on heads only twice out of 10 tosses. That means that the probability of it landing on heads, empirical probability, is 2 divided by 10. Can you see how this is different from the theoretical probability of 0.5? We have 2 types of rules that we can use probability, the additive and the multiplication rule. The multiplication rule should be used when the question includes an and. So for example, what is the probability of drawing out a king and it will be red? You will then take the probability for those 2 events, the king and a red card, and multiply them with each other. The second rule is when you have the word or. What's the probability that I will draw out a king or a jack? I then take the probability of getting king and I take the probability of getting a jack and I add them together. Lastly, the area under the curve of a frequency distribution can translate into the proportion or the probability. So in other words, if you had to take a table and calculate the probability for each event happening, so the probability of out of 10 tosses of a coin getting 1 head, 2 heads, 3 heads, 4 heads, and so forth, and you calculate it from the fewest numbers of heads to the highest number of heads, and then you plot it on a distribution, the area under the curve is equal to the probability. So the best way to understand this, or an example of this, is in your textbook. It's in the chapter about probability. That's chapter 5, and you can see it on page 80. What we will see from this type of distribution is that the events that are the least likely are the lowest bars in the distribution. The next topic that we looked at is the standard normal distribution. It's important that you remember what the attributes are of the normal distribution. It's symmetrical, it's bell-shaped, and then it can either be elliptic-curtic, mesocurtic, or platycurtic. But the standard normal distribution is a special kind of normal distribution, and it allows us to compare scores from one distribution with scores from another distribution. It's sort of like the universal language for normal distributions, and the reason why we do this is because the area under the curve for one distribution may be different for the area under the curve for another distribution. So we try to convert it to a single unit of measurement, a z-score, and this allows us to compare it, or compare scores to one another. Now, the standard normal distribution has two very important attributes. The mean is always equal to 0, and the standard deviation is always equal to 1. Calculating or converting a score from its raw form into a z-score, which is what the x-axis of the standard normal distribution is measured in, requires a formula on the left. You take your raw score, you minus the mean of the scores from it, and then you divide it by the standard deviation. But this is only one part of the solution. You then need to calculate what the area under the curve is for that z-score. And what you'll use, if you're doing it by hand, is the z-tables, the standardized tables. And you will either look at the smaller portion, the larger portion, or the mean to z portion. You can also use a manipulation of that formula to calculate the raw score, the individual score, from the p-value and the z-score. And that will be the formula on the right. If you're using Excel, you will then do norm dist and norm inv, or norms dist and norms inv. The norm dist and the norms dist calculates the formula on the left-hand side. It's calculating the area under the curve. But norms inv and norm inv is calculating the raw score. This is the z-table, and this is what you will use if you're calculating the z-scores by hand. You may also be directed to use a z-table if you're doing it in Excel. What you'll notice in these z-tables is that there are 4 columns: a z column, a smaller p column, a larger p column, and a mean to z. Once you've calculated your z-score, travel down this column and look for the z-score of interest. Let's pretend that our z-score of interest is 0.7. What I would recommend is draw a distribution, mark off where the mean is, remember the mean is 0, and then calculate or mark off where your score of interest is. So this will be to the right or above the mean. Now, this score, 0.7, cuts the distribution into a smaller portion and a larger portion, but together the smaller portion and the larger portion will add up to 1 because the area under the curve is equal to 1. Now, if the question was, what proportion of scores fall above 0.7, then you would look at the smaller portion, because look at the drawing, the smaller portion is lying above 0.7. But if the question was what proportion of scores fall below 0.7, then you'd be looking at the larger portion. If the question was what proportion of scores fall between the average and 0.7, then you would be looking at the mean to z column. Notice that if you took the value in the mean to z column for example, 0.7, a z-score of 0.7, that mean to z proportion is 0.25804. And if I added 0.5, because that is the area that falls on the other side of the mean, I will then get the larger portion. This is because the mean cuts the distribution in half. 0.5 lies on the one side of the mean, and 0.5 lies on the other side of the mean. And you can see this if you look at the table and you look at the z-score of equal to 0. There are many, many ways to ask questions about different proportions using the data in this table. I would recommend that you get used to manipulating the data and trying to answer lots of example questions so that you're more familiar with this. Also notice there are only positive scores in the standard normal distribution table, and that's because the distribution is symmetrical. So if you're looking for the negative score, you have to look for the positive z-score, and then looking at how your question is phrased, looking at how the distribution looks with your particular score of interest, decide if you're looking for the smaller portion or the larger portion. So we finally get to the topic for today, and that is linear regression, and this is chapter 10. So the whole aim of using regression analysis or linear regression is that it allows us to make predictions. So for example, you may be able to hear my stomach growling through this recording. So based on how hungry I am, you may be able to predict how loudly my stomach is going to growl. Or perhaps, based on how long Muya takes to respond to your email, you can predict how annoyed he's going to be. So we use the information from a sample of paired data to calculate a regression equation and a line, and then we use that actual regression line to make predictions about any value of y. Now the y variable, which is always plotted on the vertical axis, that is your dependent variable or your criterion variable. And the variable that's plotted on the horizontal axis, the x variable, is known as the predictor or the independent variable. This will never change. It's important that you know it. Now, in this topic, we have no interest in nonlinear relationships. And in other words, we're not interested in relationships that aren't represented by a straight line. And there are lots of relationships like this. They can be exponential, they can be logarithmic, they can be polynomial. There are tons of them, but we're not going to do it. So wipe the bead of sweat off your brow. So for regression, we typically collect paired data. This is unlike a design where you have two groups of participants who you are then comparing on a single variable. For example, you have a group of men and a group of women, and you measure the men's weight and the women's weight, and you compare those two. What we have instead is a single sample group, and we're looking at the measurements on two variables for that sample group. And this will tell us if there is a relationship between those two variables. So for example, in this one, we're looking at how afraid people are of intimacy and how long they've been in a relationship. One would assume that the longer you've been in a relationship, the less afraid you are of intimacy. Whereas the shorter you've been in a relationship, the more afraid of intimacy you are. And fear of intimacy is measured on a scale, and the higher that the score is, the more afraid you are. And length of relationship is measured in years. So what you'll see here is that participant 1, their data for fear of intimacy is 54.4, and the length of their relationship is 1 year. But for the second participant, the fear of intimacy score is 29, and the length of their relationship is 13 years. And for the third participant, it's 21.7, and the length of their relationship is 18.1. It would make very little sense to pair the first person who's only been in a relationship for 1 year, to pair that data, the length of their relationship, with the fear of intimacy score of participant 3. It has to be paired with the same person. For example, it's like if you go on a diet program. If you go on a diet program, you'll measure the before weight and the after weight, because that's the only way that you're going to know that you've actually lost weight. It makes little sense for you to take my before weight and then compare it to your after weight. For all you know, I weigh more than you do, and it might actually look like you put on weight from the diet program. So that's why the data is paired. It's paired with one participant. Now we can take that same data and we can plot it onto a scatter plot, and this really allows us to get a visual representation of the relationship between those two variables. So what you'll see on the scatter plot is the x-axis is labeled as the fear of intimacy, and the y-axis, the vertical axis, is the length of the relationship. and there are a number of blue dots here. Now each dot represents a single participant, and it represents the relationship between that participant's scores on the two variables. It's where those two variables are intersecting, so to speak. So if we look at the score on the left, that score on the left, if I had to dot a little line down to the axis, their fear of intimacy is roughly about 12, 11, and their length of relationship is about 11. So this person's been in a relationship for about 11 years, and their fear of intimacy is about 11. Whereas a score on the right-hand side, this score has the highest fear, this person has the highest fear of intimacy. Their fear of intimacy is about 55, and the length of their relationship is about 1. So can you see that each point on the scatter plot is representing a single participant, but it's representing two pieces of information. It's representing their score on the one variable, and it represents their score on the second variable. What you can also see on the scatter plot is a bold black line. Now this black line is demonstrating the relationship between these two variables. And this line is sort of like, imagine if you had to go to, I don't know, Spur, and you had to do those connect the dot drawings. Now this line is acting like that. It's trying to show where best the relationship between these points lie. It's the smallest distance between all the points. So what we typically do with this data is we fit a straight line to the data points, and that straight line is supposed to give us an idea of how well the two variables are related to each other. So for example, if you look at the scatter plot on the board, there is a red line that is going through the scatter plot from the bottom left corner to the top right corner, and there are blue data points exactly on that red line. And what that means is that because that straight line was able to fit all the data points, and the data points sat exactly on that red line, that relationship is perfect. The one variable is moving in exactly the same way as the other variable is. Okay, they are very strongly correlated with each other. Just out of interest's sake, if you only had two dots, so for example, if on a piece of paper you drew two dots, you would always be able to connect them with a single line. You'd always be able to fit a straight line to only two dots. So it is always possible to have a perfect relationship when you only have two data points. But it would be much more difficult to fit a straight line if you had 3 data points, or 4 data points, or 5 data points. Anyway, so if you look at the example on the board, what you'll see is that the way that the data points are changing in the scatter plot is as the blue dot is moving right along the x-axis. In other words, as it is increasing along the x-axis or in the x variable, it is also going up along the y-axis, and it is increasing along the y-axis. So the data point is moving in the same direction for both variables. It's increasing on the x and increasing on the y, and that means that it's a positive relationship. If the data point was decreasing on the x and decreasing on the y, then that would also be a positive relationship. The reason why it's perfect is because the blue dots are lying on the red axis, the red line. So here's another example of a scatter plot. What you'll see in this case is that the points, as they move along the x-axis, so I'm looking at the first point, which has an x value of 1, the second point has an x value of 3, the third point has an x value of 5, and the fourth point has an x value of 7. As the x value is increasing, the y value is decreasing. So the two variables are moving in different directions. That is called a negative relationship. And the reason why this is perfect is because those 4 points are lying exactly on that red line. That red line fits the 4 points perfectly. So let's take a look at the next scatter plot. So let's look at the data on the left in the table. You'll see for the variable x, the first person got a value of 3, and then on variable y, they got a value of 6. Now that's also the first blue point on the scatter plot. The next person got a value of 5 on the x variable and a value of 5 on the y variable. The third person, 7 and 8, and the last person, 9 and 6. And if we look at these data points on the scatter plot, we'll see that they're not lying as close to the red line as the previous scatter plots were. And that's because this is an example of a weak relationship, where the two variables are not correlated as strongly with each other. They don't have a very strong relationship. They're not behaving as predicted. So let's talk about straight line graphs and linear functions. So this line that we've plotted through our data points is a straight line, and straight lines have a formula which is y equals a plus bx. I think you should know this formula off by heart. Now what the a represents is the y-axis intercept, and the b is the slope. So what you'll notice in the example below is that you've got two data points and there is a straight line that's connecting them. Remember what I said? You only need a minimum of 2 data points in order to get a perfect relationship, because look, both data points are sitting on that straight line. So if we look at the A, which is the y-x intercept, this is the point on the y-axis where the line is intercepting it, or where the line is crossing or touching the y-axis. So this is the blue data point on the bottom left, and that blue data point has the coordinates 0, 3. And the way that you read those coordinates is that the 0 is the point on the x-axis, and the 3 is the point on the y-axis that correspond to that data point. So when x is equal to 0, the y-intercept is equal to 3. So this is where the straight line is cutting the y-axis. The slope, on the other hand, is equal to the b, and this is basically like the gradient of the straight line. And what this slope means is it tells us how much the y is going to change by every unit increase in the x. So for example, when x increases by 1, then the slope will tell us, the gradient, the b, will tell us by how much the y will increase corresponding to that. So the regression line that we plot, which is supposed to fit which is supposed to be the best fit for the data points in the scatter plot, is also known as the line of least squares. Now the problem is that often in our research we never, I don't think I've ever seen an example of where we've studied a perfect relationship between two variables, but instead what we try to do is get an estimate of what their relationship would be like with our actual data, and hopefully this is a demonstration of how the two variables should be related to each other. So for example, if you look at these two variables, which are height and weight, you will see that this looks like a positive relationship in the graph, and we can see that because as the x-axis is increasing, so is the y-axis. And some of the data points are quite far from the line, but some of the data points are very close to the line. So this may be quite a good fit for how the data is related to each other. Now the reason why we call this a line of least squares is because it's very similar to the way that we think about a standard deviation. So with a standard deviation, or the variance, we're looking at the average distance between each point and the mean. And remember, some of the points lie below the mean and some of the points lie above the mean. Now in this data, it's almost exactly the same. So if you look at this, the red line is the regression line, and you have each point on the line, each point in the scatter plot, and you can see where they are connecting to the line. Now the red line is supposed to be representing what the predicted y value should be given the value of x, and what we do is we calculate the difference between each data point and what its point should be on the red line. So for example, if you look at the point on the left, which is 82, we are calculating the difference, which is represented by that black line that is connecting the blue data point with the red line. Now, that distance is sort of the same as the distance between each raw score and the mean when we're calculating the variance and the standard deviation. So the further away that the point is from the line, the worse the relationship is between the variables. But the closer it is to the line, the better the line is fitting the data points. Now, just like the variance and the standard deviation, some of these points are lying below the line and some of the points are lying above the line. That means that this black distance, for some of the points, it will be positive, and for some of the points, it will be negative. So what do you think would happen if we were to add up the positive and the negative differences between each data point and the red line, which is representing the predicted values? It should be equal to 0, right? Just like we have when we calculate the variance and the standard deviation. So what do we do to work around this? We square those differences. Now, the line of least squares, in other words, this red line, it's known as that because when you sum all of those differences, compared to other ways of calculating this average distance that we are squaring, this red line, based on the difference between each data point and the red line, it gives the lowest value of squared distances. Therefore, it is the line of least squares. So this regression line that we plot through all the data points is also known as the line of best fit. And we call it that because this line is supposed to fit the data best. So what does it mean to fit the data? It means that the distance between each data point and the regression line is the smallest that it can be. So let's take a look at the data so we can understand this better. So here's the scatter plot. You can see the blue data points are on the scatter plot. The regression line is red. And then there's a small thin black line that is connecting each data point to the regression line. You don't need to have these small black points on the line. It's just to make a point, okay? It's just to make a point about how the data connects. So what we can see, for example, is that there are 3 data points that have very large, long black lines, 120, 72, and 82. And what that means is that there's quite a big difference between that point and the regression line that it is being fit to. Now that black line is known as the residual. It's the difference between each data point and the regression line. Some of the data here, though, doesn't have a very long residual. So 68, 70, 74, they all lie much closer to the regression line than 82, 72, and 120. In other words, their residuals are smaller. They are fitting the data, the regression line much better than some of the other points. So what I want you to notice as well is that the regression line is predicting what the value should be for that x value. So let's take the blue data point that has the value of 120 next to it. That 120 can be mapped onto the y-axis. But for the x-axis, its coordinates are probably 210, 120. We can check the data later. Now, the regression line is predicting, though, that for a x value of 210, there should be a y value of maybe 108, I'm guessing. So the black line is now the difference between what the predicted y value is on the regression and what the actual y value is on the data. So it is a measurement in y space, so to speak. It's a measurement on the y-axis between these two y coordinates, the predicted y and the y of the data point. It's very important that you know what a residual is. So this line, this regression line, takes the form of y equals a plus bx, and this basically defines what the regression line is, or what it will look like. Now we're going to solve for a and b using well-known formulae. Remember, a is the intercept and b is the slope. So we will calculate a and b using the formulas below. I think you should be familiar with these formulas. You will be introduced to them in the tutorials, but what's important for me is that when you're sitting in the exam or you're sitting in the test, you should be able to look at this formula, relax, and solve it. So the formula for B is the covariance of x and y as the numerator, and we are dividing that by the variance of x. And to calculate a, we take the average of y and we minus the product of b multiplied by the average of x. So what this means though is for the formula for b, you first need to calculate the covariance of x and y before you can move forward and continue. So what in the world is covariance? Now covariance refers to how the two variables are varying or changing together. So in other words, as the one variable changes, how does the other variable change? Now positive covariance means that the variables are positively related. So in other words, as the one variable increases, the other variable is also increasing. Or as the one variable decreases, then the other variable is decreasing. So they are moving in the same direction together. Whereas a negative covariance means that they are inversely related. So as the one increases, what do you think will happen with the other one? It will decrease. So let's look at the following pairs of data. We've got three, I don't want to say pairs, let's actually say sets of data. So we've got three sets of data. In each set, we've got 4 pairs of data. So for the first set, we have x values 1, 5, 7, 9, and y values 11, 15, 17, 19. For the second set, 9, 7, 5, 1, y values 1, 5, 7, 9. And for the third set, 3, 5, 7, 9, and y values of 7, 5, 5, 7. So if I asked you, what are the data, or what is the data for the first pair in the first set? So the first person got a 1 on the x variable and an 11 on the y variable. Remember, for regression, we collect data in pairs. So there are 2 measurements, one on the x, one on the y, and they are paired together. So let's do another example. What did the second person in the second set get for the x and the y variable? 7 and 5. Okay. Now what you'll notice perhaps with the first 2 sets of data is that they are related to each other. As the x variable is changing, so is the y variable in a specific way. There seems to be a relationship. With the first set of data, as the x variable is increasing from 1 to 5 to 7 to 9, the y variable also increased from 11 to 15 to 17 to 19. So there is a relationship, there is covariance, and in this case it's positive covariance because the variables are moving in the same direction. With the second set, what is the x variable doing? It's decreasing. It's going from 9 to 7, 5 to 1. However, as that x variable is decreasing, what's happening with the y variable? It's increasing. So they're both moving, but they're moving in different directions. So there is covariance, but it's inverse covariance. So this is a negative covariance. With the last set of data, there is no relationship. There is no way to predict how those 2 variables are moving together. So what you'll see is that as x is changing, so is y, but it's not predictable. So let's take a look at the formula for covariance. So just like variance and standard deviation, there are 2 formulae available to you. You can choose whichever one you want to use. I find the one on the left is slightly easier for me to remember, so that's why I prefer to use that one. So if we look at that formula, what you'll see is that we're calculating the difference between x and x bar, and we're calculating the difference between y and y bar, and then we are multiplying those 2 differences with each other. We'll then do that for every single pair of data. We'll then add up all of those products, okay, of the differences together, and then we will divide it by n minus 1. Now, if you had to imagine that you've got a distribution of data and you are calculating the difference between each individual score and the mean for that variable, obviously, if your score is very far away from the mean, so for example, if my x score is very far away from the x bar, so the average of x, and my y score is very far away from the y bar, or the average of y, then the distance between x and x bar and y bar will be very large. Now, when I multiply those two very large numbers with each other, that product is going to be extremely big. Okay, so remember, we are collecting data in pairs. So each x score is paired with a y score. Now, if both the x and the y are for the pair of data are both very far away from their respective means, so the x is very far away from the x bar, and the y for that pair of data, that y is also very far away from the y mean, then the product of those two differences is going to be very big, and it's going to be much, much greater than if they weren't simultaneously as a pair very far away from their means. So this is an important thing to note about this formula. Sometimes it's really difficult to look at these formulae and understand what they mean, especially when you take it step by step. But basically, an easier way to think about covariance in terms of the formula is that it is like an average simultaneous distance of the x and the y scores from their respective means. So like the average formula that we've worked with earlier, where you sum the scores and then divide it by the number of scores, or the standard deviation, which is like the average distance that each score is from the mean. So you sum each distance, squared distance, divided by n minus 1 if it's a sample, and then you square root that. This is now the sum of the product of the distances between each x and y score from its respective mean, divided by the number of scores of n minus 1. So it's like an average simultaneous distance. Now in Excel, there are 3 different types of formulae that you're going to learn about. The one is covar, the other one is slope, and then intercept. So it's really easy, I hope, to guess what the slope function is going to do. That's obviously going to calculate the slope. That's the B of the formula. The intercept is going to calculate the A of the formula, and then the covar, which is for the population only, is going to calculate the covariance. The one thing is that for a regression equation, you can only predict y variables, and this is standard. We're predicting y variables from the x variables. So if you want to identify an x variable instead of a y one, because remember the formula is y equals a plus bx. Now if you wanted to calculate what x would be, then you will need to rework the formula and then recalculate everything. Okay. So let's do an example of regression. So we've got pairs of data. Remember what I said about how to read these data points? The point is x, y. So for the first pair, it's 1, 3, then 2, 5, 5, 7, 4, 6, and 7, 10. And what we've done is we've plotted each of these data points of paired data in the scatter plot. So you'll see for the first pair, that's been written 1, 3, that's the most left blue data point in the scatter plot. So just by looking at the scatter plot, we can kind of see that there might be a bit of a pattern. What do you think is happening when you look at these points? How are the two variables changing together, if they are changing together? I think they're both increasing. It looks like it's a positive relationship. It looks like a very strong positive relationship, actually. So what we're going to do now is draw the best fitting line through these points. So remember the line, that the straight line that represents the regression is y equals a plus bx. And we're going to solve for a and solve for b. Before we can calculate either of those two, though, we first need to calculate covariance. And this is that hairy formula, the first one on the slide. It's easier to calculate this if you're using Excel, because you'll very easily be able to calculate that product between x and y and then the sum of all of them, and then also to calculate this. So don't worry if you can't do it by hand on a piece of paper. You'll learn how to do it in a tutorial step by step. But basically, if we were to calculate it, we would then put the values into the numerator at the top, put in the denominator, it's n minus 1, so it's 4, and we get a covariance of 6.05. Now this covariance is positive, which means that both variables are changing in the same direction, and that was evident in the scatter plot. We could see that there was a positive relationship. We then take the 6.05 and we put it into the top of the B formula, the numerator, because the B formula asks for the covariance at the top. So once you've put that in, it's 6.05 divided by the variance of x. And the b, the slope, is equal to 1.0614. So what does this mean? This means that as the x value variable, when that variable increases by a unit of 1, the y variable will increase by a unit of 1.0614. Then we're going to calculate the intercept. In order to do that, we get the mean, the y for y, and then we plug in, or we replace the b with the slope, which we just calculated now, and we multiply it by the mean for x. And what we get as the intercept is 2.1667. So if we go look back at our scatter plot, here is the data points with the regression line through it. Don't worry, you're not actually going to plot the regression line itself, in other words, by hand. The computer will do it for you. But what you can see is the scatter plot, the regression line going through the data points, and then the formula for the regression line is in the top right-hand corner, and it says y equals 1.0614x plus 2.1667. So remember, the equals 1.0614x, that is the slope. And the intercept is 2.1667. And we can see that if we look at where the line is touching the y-axis, that is at the point of 2.1667. And there you go, you have a regression line.